Hello, everyone. Thank you for attending today's webinar titled Increasing Your Product Development Success with Graphene Additives, brought to you by Composites World and presented by MITO Materials Solutions. I'm your moderator, Scott Francis, editor of Composites World. Today's presentation will last approximately 30 minutes, followed by a question and answer session. If you have a question, you can type it at any time during the webinar in the Q&A section of the chat. The webinar is being recorded and when complete will be made available to you via Composites World. Our presenter today is Kevin Keith. Kevin is the CTO and co-founder of MITO Materials Solutions, a material science company focused on building a more sustainable world through high-performance materials. MITO is the first to market proven functionalized graphene products that deliver lab-verified improvements in strength, durability, and flexibility in composite materials. Kevin, I'll hand it over to you.
Awesome. Thanks, Scott. Thank you, everybody, for taking the time today to sit down. I do appreciate kind of think through some Q&A, some questions that you really want to answer. We're going to be diving into a lot of different data and different scenarios today, because at MITO Materials, what we're aiming to do is build a stronger, better world with the materials and material chemistries. So generally, everybody's trying to move towards decarbonization, as we all know, and hydrogen long-haul trucks is one of the best methods to do that. They're very necessary for decarbonization, and hydrogen is a very favored fuel for that because of its high energy density. Now, the problem with that is that the carbon fiber is booked out until 2026. Windmills are also necessary for decarbonization. The problem with that is that the US alone would consume all of the world's supply of carbon fiber. And so MITO Materials saw this problem, and we realized that there was one of two ways to really solve that. And it was either more carbon fiber needs to be made, and if they're already capped, then there's really not much else that can be done there, or you can do more with less. And so with our additives and our chemistries, we're able to make carbon fiber composites up to 100% stronger at extremely low dosages. So you can use 20% less carbon fiber, and then that way, across the globe, you can reduce the amount of carbon fiber used by 38,000 metric tons. Now, we do this by functionalizing a material called graphene. So graphene, I hope everybody is aware, but graphene is a family of materials. The ISO standards that are going into effect hopefully next month is going to qualify this as graphene-related 2D materials, or GR2Ms. Graphene has a lot of different buckets for characteristics. Mainly, graphene is considered graphene when you have anywhere between 1 and 10 layers of carbon stacked together. And these SEM images are all different types of graphene, made from different manufacturing methods and exfoliation processes and chemical methods. So morphology, a lot of the time, it dictates the integration and performance of this particle, and as well as the system that you put it into, whether that's based on mechanicals, thermal, electrical, which then stem into other applications. The sources, you can go from graphite down to graphene, or you can even go from a waste gas into graphene, and I'll get into that a little bit later. And those two things really dive into the compatibility of the graphenes. So the compatibility is driven not only by the morphology and the sources, but by the defects and the residuals and the crystallinity. And so in my world, there's no such thing as a bad material most of the time. It's that there's bad applications for the material. And so when we get these feedstocks in-house, MITO Material functionalizes on top of that. So what we do is we create these chemistries using graphenes, graphene oxides, graphites, GR2Ms, if you will, and we can do this on any feedstock. We have patented chemistries with a vast array of company trade secrets, and we toll everything out. We're the first and only one that can actually functionalize graphene, verified by the Graphene Council, an independent third party. And so with that, we're able to toll all of this out and make it anywhere in the world. And right now, our tolling suppliers, they can make collectively a metric ton, but at the loading levels, that can make 1 million pounds of polymer. And so it's a lot of talk, a lot of words, but really what this means in practice is that you're able to turn these graphenes into a better dispersible system. So here are 3 different feedstocks made from tops down and bottoms up, so graphite or cracked gas. And on the left in the yellow is our material functionalized on top of that feedstock. So we made a chemistry to go on top of that feedstock. And you'll see here, it disperses much better into isopropyl alcohol using just a magnetic stir bar. This is really unheard of, and we're the ones that have cracked the code to make this a reality in the marketplace. Now, when you plug this functionalized material, these GR2Ms, into a customer system, and what we found is that when you're comparing graphene, a bottoms-up graphene, or a nanographite, which is a material that has more than 10 carbon layers, and it's usually considered really chunky, think pencil lead, those are really hard to disperse and to get integrated. And so in order to do that, we actually had to 3-roll mill everything because they just disperse so poorly. Our chemistries and our functionalization, the way that we tailored it to this system, we could do a shear mix, but that wasn't cutting it for the other ones. And so you'll see here that whenever you actually do the formulation with the GR2M, the graphene material, and you pick the right buckets to go into the system, you get the property increases that you're really looking for instead of trying to brute force your way through it. And most customers that I talk to, they have tried graphene or they've heard horror stories of graphene. And whenever people have tried graphene, I would say probably 99% of the time, they've been burned by it. Most people, they've spent millions of dollars, a lot of time and effort trying to source and qualify graphene. And even then, that 1% that gets it over the line, most of the time they have a feedstock issue. So when you're able to formulate on top of the graphene material and you understand the buckets that you need to fill, you can start supplementing that one supplier, and you're able to branch out and make 2-3 different suppliers fit within your range of what you really need. And so today we're going to cover a couple of key topics. So number one, you need to make a proper DOE. You'd be very surprised at how often really good scientists miss this when it comes to testing new additive materials. Second one is that we're going to look at various forms of graphene or GR2Ms. Then we're going to tie that into papers and the forms of the graphenes used. And then we're going to deploy those papers, all the information that we're going to learn today, into commercial deployments. So things that are actually being used in the market space within our realm, because we're able to source all of these other graphenes, functionalize on top of it, and deploy it into certain applications because we know what levers to pull when it comes to these graphene materials. So number one is please plan ahead. I don't know how many times we iron out a DOE and people don't necessarily understand that you need to do a ladder study. Graphene is one of those interesting materials that you don't get more the more you load it up. So if you're looking for a specific mechanical property, generally, if you're breaching the 1% realm, you're not going to get that mechanical property, but you're going to start getting some other interesting properties you wouldn't have expected, like damping properties, electrical or thermal conductivity, or insulation, depending on which graphene material you chose. And usually, I suggest that you do this in a controlled but simulated manufacturing environment, because in my experience talking with my customers, the times that they have tried graphene and have been successful at doing a really good design of experiment, when they scaled from a benchtop system, they didn't really correlate it to the production method. That's because it was in a very controlled environment that when you go into production, there's more entropy and chaos involved than what you can do within a fume hood. And so with these materials, you can always do more with less. You can start getting some really great strength properties depending on the graphene material you plug in, all the way down to 0.05, 0.03, sometimes 0.01% by weight of the resin. So it's legitimately just a sprinkling of this material into the polymer, and it gets the benefits everybody's looking for. Now, There's a lot of different forms of graphene, and these are all the graphene promised properties that a lot of people really like to look at and tote about. That it's stronger than steel, it has a high electron mobility, like a lot of different things that the graphene itself, yes, it does, but I typically don't look at it as what the property of that graphene is, but what it can actually introduce into the system. So some forms of graphene has high UV resistance, other forms flame retardancy, flexibility. The list can go on and on and on. It's that you have to pick and choose which metrics you want to measure in order to kind of source what graphenes and what morphologies you really want to look at. So in order to make a graphene, there's a couple of different ways you can do this. One is called a tops down method. So tops down is when you take graphite, so think pure carbon, 85, 99.9% carbon, anywhere between there, depending on what your feedstock is, and you're able to do a couple of different things with this. You can do mechanical exfoliation, where people send it through a grinder. You can do mass amounts of this, but you're still making graphite. Graphene nanoplatelets, if you will. It's smaller chunks, but you can't control the morphology, the layer counts, the defects. You're just regrinding it up into a powder. Then you have a chemical treatment method to where it then splits off into two different methods. You have graphene oxide, to where you're putting it through a chemical bath and you're oxidizing the graphene and you're blowing those layers apart. Another one is that you can pair mechanical and chemical exfoliation to get those layers apart. You can still grind it up. It's in a wet process, but you can still more effectively control your layer count. And then beyond that, you can exfoliate it, reduce it, do some other treatment methods to that, and then you get these graphene materials. Another method is what we call bottoms up. Bottoms up is when you take, you can grow it, you can crack it, you can take waste streams and you can blow it apart. So think like methane, CH4, acetylene. You can start doing really high temp processes on this to be able to blow it apart. And whenever that happens, the hydrogen forms itself, and then the carbon, it forms together. And when you crack enough of this, graphene forms. So this one has a lot of other interesting intrinsic properties as well that you get differently from other feedstocks. So no matter which path you take, you can still get to graphene, but we have to understand what form of graphene is really going to come out depending on what your input is and how you process it. It's like anything else in the world. And so graphene can be applied to a lot of different materials. Definitely not going to read all these, but it's broken up essentially into three different categories. You have single layer in the orange right here. You have single and multi-layers, so anywhere between 1 and 10 layers. 1 and 2 layers, and then bulk graphene, which between 2 and 10 layers, that's considered bulk. This is only for graphene, not nanoplatelets or graphite. Graphite can go into batteries and supercapacitors. They are currently, but there's a lot of other intrinsic problems that I will not get into today whenever it comes to getting graphite into those battery anodes. So because of the different forms of graphene, you have a number of defects that are introduced, and you have a number of layers, kind of depending on what method is used to make the graphene. It can control a lot of different methods. So like I said, the liquid exfoliation, you can have a really low number of defects, but you have a really high number of layers. Mechanical, you still have a higher number of layers, but because you're just chewing it up, you're going to introduce a lot of different defects to that. So typically, range for the higher value products, so think like carbon fiber composites, coatings, CVD, that type of thing, you want to stay within this red box. So the fewer the layers, the higher the price per kilogram. So if you're looking to do like a monolayer graphene to go into your fiberglass polyester system, it's not going to work just on a cost perspective. That's because usually whenever it comes to monolayer graphene, they're charging about $1,000 to $2,000 per gram. It's a lot. It's insanely expensive. But of course, every production method has its limitations, because if you're trying to get that monolayer graphene, you're making nowhere near as much. But if you're sending chunks of rock through a grinder, you're going to be making a lot more, albeit at a much, much lower quality. But there's a reason why some graphenes in the world are being sold for, $300 a kilo type of thing. And so I know I mentioned earlier about the number of sheets that make up the graphene. It kind of falls into different product descriptions. So whenever you have one layer of graphene, that's considered monolayer, and anything above that is kind of considered bulk. So you have bilayer, trilayer, and then few layer graphene, which is the realm that most of my customers tend to hang out in. Monolayer, few layer graphene has some really good properties that you're able to kind of tailor towards, and anything more than 10 is considered nanographite. Very chunky, dense material. It's not a bad material, but you have to realize what that chunky, dense material can really be plugged into, and start adjusting your expectations that, hey, if I try to disperse this into a resin that has 9,000 centipoise, it's not going to go well, and it's going to crash out eventually. So just have to adjust that expectation of how you're going to apply that really chunky material. And so generally, the Graphene Council, they did a study across their 3,000 members. Some of them are graphene producers, but a lot of them are consumers, to where they're interested in graphene. They really want to look into it and be a part of it. But most of the time, the main barrier to entry is the cost and price. And that's because we're trying to educate everybody that, hey, different grades kind of have different price points. So we need to talk about how you really want to start deploying these materials and what metrics you're looking for. Another part is that the production methods, scaling, and distribution. Tops down versus bottoms up. It can vary a lot of different things within the product itself. And so being able to educate people and help people understand that when it comes to these different methods, it really does matter to how much you're really paying for that product. And so within the current industrial uses of graphene, surprisingly, a lot of them are within composites. Most of the graphene that's being deployed into the market space right now, 48% of that is within composites. Composites, anything between carbon fiber, fiberglass, thermosets, thermoplastics, it's being integrated into a lot of different things. Sheet molding compounds, bulk molding compounds, list goes on and on. Some of them are also being used in energy storage. There are battery manufacturers out there that are using, I believe it's few layer graphene to go into their battery system, and they're pairing that with silicone because of the properties that their few layer graphene shows when it's paired with that silicone, to have that dimensional stability whenever you go through a rapid charge and discharge of that anode. That way it maintains the integrity, but it also has a higher throughput and output of these electrical devices. So going through a couple of different papers, as well as the forms that were used. So here we have a system that's used with thermosets. It's a nanographite oxide made from a chemical exfoliation. And so what they did is they sonicated into this thermoset at 0.2% by weight. This graphite oxide was a nano powder. And so by the time they got it integrated, you can see here that as you start increasing your GO concentration, you get more and more, but then at some point, it's going to start very much degrading. At the 0.4%, you generally see a much higher, but even then, you're only getting maybe about a 10% increase for that amount of loading. So by the time you start getting higher and higher loadings, because you're choosing a graphene oxide to go into that system, you're getting a lower heat flow. So graphene oxide is an interesting material in the fact that, yes, it's graphene, it's within that GR2M, but because of the properties and the characteristics that it shows, it's more insulating. So you're able to kind of see that, hey, if I'm trying to hit some certain properties for mechanical performance, I can start looking towards what other GR2Ms are out there of how I can deploy that and really get the metrics that I'm looking for without overcomplicating things. Another paper, they put various forms of graphene into an epoxy within a thermoset, and this was without fiber reinforcement, so just pure plaques. And so here you'll see GNPs are graphene nanoplatelets, FGNP are functionalized graphene nanoplatelets, and then you have FGR, which are functionalized graphenes. So when you go through a standard 3-roll mill method, I would really like to point out here that you'll notice that the GNPs are loaded at a much higher loading, and they get nowhere near as performance values as the functionalized systems or the functionalized graphenes. That's because whenever you try to put pencil lead into a thermoset, even if you're trying to do a 3-roll mill, sonication, whatever it may be, it's still pencil lead. So I really like this study because it was really showing everything side by side of how it really compared to these nanoplatelets, graphenes, and functionalized systems, that when you start adding the chemistries on top of it and knowing what to plug into the system, you actually start getting these huge increases at extremely low loadings. Another paper, they introduced graphene into nylon 11 and 12, anywhere between 0.1 and 0.1 and 3% standard compounding. And so what we saw is that the Young's modulus in one nylon really worked at a really high 3% loading, but you saw it still improved the values 10-15% at the 0.1 and 1%. It kind of looks like a little bit of a bimodal bell curve, and the fact that it jumped when you went from 0 to 0.1, it dips 0.3, 0.6, and then it jumps back up at 1%. And that's because of the metrics that you're using to qualify what that few layer non-oxidized mechanically exfoliated graphite was enacting on the system. Nylon is a really interesting material in the fact that when you load graphene into it, it can get really touchy depending on what graphene material you load into it. So you have to really watch out what you're putting in there. Same thing. So here you'll see those graphs that within nylon 12, 0.5, 0.1%. This is the same graphene material loaded into both of these plastics, but you still get drastically different properties, even though you know what levers are being pulled, but then it's interacting totally differently with the system because of how that graphene is made. So taking it from academic to commercial, here at MITO, with our functionalized additives, what we've done is we've gone into sports and transportation sectors, as well as some infrastructure, but I really wanted to highlight a couple of key points that we're in right now. One of which is St. Croix. They are the most highly engineered fishing rods in the world. And so what we've done is that we functionalize a fewer layer graphene oxide, so made from an oxidized graphite. And so when we were put into their system, they have their own internal testing to where they test sensitivity, recovery, and strength. The strength test that they do, all three of these tests are on a rod within a dynamic scenario. So when they test sensitivity, they hook them up to extremely sensitive load cells, and they have a pneumatic hammer hit it, and they measure how the frequency moves back and forth and how much time it takes to reset to zero. The recovery method, what they do is they hook it into an anchor, they load it to a predetermined amount, and then they let go, and then they measure how fast it goes back to zero. So that one's more of a tournament style bracket. And then strength, they hook it into a dynamic load cell to where they simulate hook setting at varying degree angles. And so by the time you're able to calculate how much momentum force is going into the system, that's how much extra strength is being calculated. So you'll see here that at 0.05%, between 0.05 and 0.1%, you still get an increase at 0.1%, but nowhere near as 0.05. And then by the time you load 10 times more material at the 0.5, you're back up at that extremely low loading level. But because of the morphologies and the characteristics of this functionalized few layer graphene oxide, made from exfoliated oxidized graphite, we knew that there was going to be damping properties the higher the loading value you got. And then we knew that the strength at the 0.05% was going to be much higher than that 0.05. So there's trade-offs that you can do here depending on what chemistries and morphologies you want to put into the system, depending on what your goal is. And for a comparison, Epic fly rods does have graphene in them. And if I recall correctly, they're loaded in at probably 0.75, 1%, somewhere in there into the fishing rod. And even then, their percent improvement was between 1 and 8%. And that's because more likely than not, it was graphite. It was chunkier whenever Epic fly rods introduced that material into their line. There weren't standards around what graphene is or isn't. So a lot of people got away with a lot of different stuff that people will no longer be able to do because we're going to be tying syntaxes to it in order to say, hey, I want to source XYZ, and this person, and this person makes something like that, but that one doesn't. Another commercial development that we've done is that we've taken a functionalized few layer graphene made from a waste process, so a bottoms up graphene. We did some extra chemistries with it, and we made a sizing solution that plugged directly into carbon fiber sizing for recycled carbon fiber, dispersed reactively. It's a water solution that's shelf stable. Right now we're up to 8 months. So when it was sized onto the carbon fiber at extremely low loadings, less than 0.5%, then that fiber was put into a nylon 6 at 20%. So all in all, the graphene's weight by the total end composite was about 0.02, 0.03%. With just this product, we were able to increase the nylon 6 performance, unnotched impact by 37%, flex strength by 18%, and the tensile elongation by 50%. That's because when we looked at our recipe book, we looked at our feedstocks, we understood, oh, we're looking for these metrics that we want to increase. And so we looked at the morphologies, we looked at the characteristics, we paired it with some other chemistries that we then deployed into the system to increase the interfacial adherence between the fiber and the polymer. That's why we're getting that tensile elongation increase so high at that 20% loading. If anybody's familiar with nylon 6, it's a very brittle material. And the fact that we were able to do a 50% increase in tensile elongation with such a little amount of material, that's because we understood the recipe book we were looking at. Another use case is that we deployed a functionalized few layer functionalized graphene oxide made from a mechanical exfoliated graphite. A lot of words, but essentially this graphene oxide was made from a chemical and grinder process to be able to blow it apart. We functionalized on top of it and it was put into a transportation application. We chose this material because it's a vinyl ester system within our transportation, so we had to meet cost. And so when we put our chemistries into it, it reactively dispersed into the resin. And these results here are at a 0.1% by weight concentration within the vinyl ester, put into a preformed fiberglass mat. It was an e-glass mat, tested the ASTM standards. And so what we saw is that with this little amount of material, we were able to increase the flex peak load by 105%. That's a massive amount. So to the point that you're able to actually you can do one of two things. You can either take this fiberglass system and you can use less, a lighter material, use less layers, whatever it may be, or you can officially transition a lot of these other metal systems to this fiberglass system. So because of how we understood how we wanted to deploy materials, what morphologies we really wanted to look at, we were able to deploy something successfully into the transportation market space. So I want to thank everybody for taking the time today, and I look forward to your questions. Thank you.
Thanks so much, Kevin. Just as a quick reminder, if you do have questions, you can put them into the Q&A section of the chat. The webinar is being recorded and when complete will be made available to you via email from Composites World. Kevin, we have a few to get started with here. First off, do you have a battery grade graphene for battery manufacturing?
Yes, we're working on a couple of different applications and feedstocks right now. So just be clear, we don't make the graphene, but what we do is we source the graphene and we functionalize on top of it. So because of our position in the market space and our industrial know-how, is that I do know which graphenes to source for a battery application. And then whenever it comes to battery chemistries, I work with a partner to say, okay, what systems are you working with? What's your specified needs? And then we're able to formulate to their needs on top of that battery grade graphene, if you will.
So I'm going to try and do this question justice, but and I think you touched on a couple of things that might be around this, but I'm going to read this. What are the different functional groups that you incorporate in graphene? They're asking about functionalizing graphene with amine or anhydride, and also with thermoplastics. I know you mentioned some thermoplastics, but they specifically mentioned PEEK and UHMWP.
Okay, so a lot to unpack there. That's a good question. So let me start like way back. So the term functionalization on a graphene, that is finally officially being defined by the ISO board. So ISO is going to be pushing out a standard that when we talk about a functionalized graphene, it's more than an oxygen, more than an amine, more than really simple chemistries that can be considered defects on the graphene. Now, getting into the meat of the question is that when we look to functionalize graphenes, it depends on what feedstock we want to functionalize on top of. If it has a dispersion problem, we tend to go for a certain particle. If it has some other mechanical variations we want to boost up, tone down, we go for another particle. All in all, we go towards more complex chemistries than just attaching an epoxide on there, an anhydride. What we look to do is we try to look at a whole library of materials, and we tend to go towards like silanes, silane particles, other more complex chemistries that can do a lot more than just attaching an NH2, NH3, an epoxide, something that can do more. Because if people are more concerned about attaching an epoxide on there, you can honestly just get reduced graphene oxide, but you're buying Swiss cheese at that point, because reduced graphene oxide is a form of a GR2M that when people make graphene oxide, they say, okay, cool, time to burn it. And they burn it all the hydroxyls and carboxyls off, and it leaves the epoxides. But then you have a highly defective structure, but you have the epoxides on there. So it generally depends really what system we're going into. Peaks, yeah, we have peak chemistries. UHMWPEs, yes, we have chemistries. We have 2 chemistries actively deployed out into the field in both of those categories.
Okay. You showed a lot of physical property data. Have you measured any changes in electrical properties?
So we have a couple of data points in terms of functionalized graphene oxide. When we put this functionalized graphene oxide into a carbon fiber reinforced thermoset epoxy, it's a 50-50 ratio between epoxy and carbon fiber. We load that functionalized graphene oxide into the resin at 0.1% by weight concentration, and it actually increases electrical insulation anywhere between 200 and 400%. That's because of the chemistries we tie onto the graphene oxide. And so while that might sound bad, you're thinking, man, that has terrible anti-static properties. What you're actually able to do at that point is you have a higher RF pass through. You don't have an EMI shield. I've talked to a couple of transportation people that they've said, hey, I try to make my system lighter. I chose carbon fiber. but I couldn't get any cell signal in it. So I had to scrap the whole project. Well, you use that additive, and then you're able to have a much higher radio frequency pass through. You have a stronger system, and you can lightweight all at the same time. We are currently actually launching a couple of pilots within the adhesive space, battery space. So we're going into a couple of different components in the battery pack with different chemistries that you're looking to increase thermal throughput as well as electrical insulation, because you don't want to short that system out. So we're gathering that data right now. I can't detail any of it, unfortunately, but yeah, we have some really good data with that.
Do you have any experience in reducing friction and wear?
None of our customers or our deployments have had that focus just yet. I'm currently working on a couple of different formulas for that application directly. So far, so good. I'm waiting to have feedback on that, but with our chemistries, we were able to make a shelf-stable dispersion that is more focused on coefficient of friction reduction.
How can graphene be mixed in powder resins, for example, rigid PVC?
Ooh, that's asking a lot. We've had powder coating manufacturers blend it the same way that they blend their powders. When you go, so if you're talking about just blending the powder together itself, you can do that. Scientist, all right, I don't know how homogeneous that's going to be because it's entirely user or machine dependent. If you compound it into the plastic and then powderize it, that's totally fine.
Okay. Can you functionalize graphenes in the size of under 1 micron and compound them into polyethylene?
So if you're sizing under 1 micron, yeah, we do that. I, for some reason, short-circuited and I heard 1 nanometer, and I was thinking that's an extremely expensive material already. But yeah, you can do 1 micron or less.
What are the typical size distribution of the graphenes?
It depends on what your feedstock is. So if I choose a graphene oxide, typically the dry powder size is anywhere between 13 and 55 microns. That sounds big, but it actually eases handling quite significantly. Typically EHS, they dictate that anything above 10 microns can be handled by a P100 mask. Anything below that is very much a health hazard, and nothing can handle that. So all of our particle sizes are by design a lot bigger, but whenever you go into the system, they disperse out much more effectively to where you're having, single digit micron systems. That's with that graphene oxide. With other graphenes, again, depending on whether you're going tops down, bottoms up, what the feedstock is, we've seen that as large as 150 microns, and we've seen that as low as 4 microns.
Any recommendation to improve dispersion of carbon black within a resin system prior to coating?
Mix it more. Carbon black is such a cheap material that functionalizing on top of it, doing any other chemistry besides sulfur, it gets really costly. Because carbon black, from my understanding, it's usually loaded into the coating anywhere between 1% and 10%. That's a lot of material. It also has a way different morphological structure than graphene. It's a lot more chaotic. So it's harder to handle. We haven't really delved into carbon black just because of the cost perspective. Nobody's really interested in adding cost to it. They're always looking for cheaper, never better.
Is there a water-free form of functionalized graphene for use in a 100% solids polyurethane resin A+B structural application?
Yeah, I have a couple of those on the shelf.
Any applications yielding improvements on friction, lower, or thermal management heat dissipation?
Gathering data on thermal management heat dissipation, so far so good. That is with a pilot customer, can't say. That one, we paired certain functionalizations, a certain structure and layer count to that. We do have some data with graphene oxide, functionalized graphene oxide, that I know I showed earlier. By the time you start loading graphene oxide higher and higher, you get more thermal insulating properties. Our chemistries were able to actually boost that up to where at 0.1% in a polyester, it increased thermal conductivity by 20%, loaded at that 0.1% by weight. So it's a much lower threshold than standard graphene. And it was just a shear mix system. We didn't have to sonicate through Romo, anything like that. Coefficient of friction, I have some people testing that right now. I have some formulas that are actually out just specifically for COF. I have seen that all of our formulations so far, whenever they're put into thermoplastics, it kind of plays into it. All of the thermoplastics that have our material inside of it, they say it cleans up better than the neat. I've seen some customers put our material into a single barrel extruder, and by the time they get to, oh man, what was it? It was 0.05% by weight. It got so slick, the barrel couldn't push enough. So it got stuck in the barrel. So it's there. It just, again, depends on what system you're plugging it into. If it's a fiber-rich system, you're not really going to see the benefits because it's more fiber-rich and it's more bumpy. But if you're looking at like a lubricant, a thermoplastic, a polyurethane system even, or a phenolic, yeah, it should be there. But again, it goes back to that DOE and ladder study that because of the system that you're using, we'll have to kind of go back to that playbook of going through the process of what are you using? What are you looking for? And then we can say, all right, this morphology, this chemistry, deploy it here. And then we can do a ladder study and then we can drill down exactly what you're looking for.
What graphene-based material do you suggest to reinforce thermoplastic matrix by melt mixing? The composites should provide high mechanical thermal properties and effective electromagnetic shielding.
Reach out to me after this webinar. There's a lot to unpack there, and I have a lot more questions.
Does MITO work on functionalization of other materials, clay, boron nitride, etc.?
Boron nitride, it's on our docket. Interestingly enough, this is going to sound totally out of left field. We've functionalized cornstarch. Sounds insane, but whenever we functionalize on top of the cornstarch, it actually reactively disperses because in certain papers, they've shown that when you just load a pure cornstarch into a thermoset composite, you get some mechanical benefits, but it's crazy hard to integrate. And so we took all of our knowledge and our playbook that we use already to functionalize graphenes. We applied it to a certain cornstarch, and by the time you load it into a BPA epoxy composite, no fiber reinforcement, so just a plaque at 1%, it increased impact resistance by 50%, and it increased flex strength by 20%, if I recall that number correctly. So long story short, yes, other additives.
Do you have experiences with mixing expanded polystyrene system with graphene?
I don't. I haven't had anybody ask that question in the, oh man, what year is it? 8 years I've been doing this, so congratulations, you're the first. I, I honestly don't know what the cost benefit of that would be. Reach out to me and we can talk.
Okay, trying to see if there's some that. Does it make a difference if we are dispersing large particle size graphene with shear mixer and epoxy?
It depends on what viscosity of that epoxy. So, for instance, yesterday I just had a 7-hour pilot where on the shop floor, mind you, we were dispersing our functionalized product into an epoxy. Typically, this epoxy is within the 12 to 18,000 centipoise. That when it's that thick at room temp, we generally say, hey, you're going to have to 3-roll mill this because it's like honey. Now, because we heated it up, it had the viscosity probably 800 centipoise, maybe 1,000. So it was a lot thinner, and we were able to just shear mix it, and it reactively dispersed. It was very, very beautiful. So you can do it. You just gotta watch out for that viscosity. Generally, I recommend if you're doing a shear mix, 9,000 to 10,000 centipoise is going to be your upper limit before you start have to get into the realm of, okay, what's my blade profile look like? Do I need to use a homogenizer? Can I just heat this up and do that? So it's definitely, it's a trick, but it's like any other additive on the market, is that I wouldn't expect carbon black to go into a 18,000 centipoise epoxy effectively. I'm going to have to heat it up and disperse it just like that.
We have a question about compliance with environmental health and safety protocols for handling graphene. Can you talk a little bit about those considerations?
Yeah, for sure. So like any other powder, standard personal protection equipment is recommended. We recommend a P1, so NIOSH, OSHA recommends a P100 mask, gloves, and smock. Generally, powder handling best practices is wide mouth containers. We ship all of our products in wide mouth, shorter containers because if you're trying to dig into a very small container and you're having to move fast, it's not going to go great. Minimal wind, preferably no wind, standard operating procedures in that regard. I've gone into some really interesting manufacturing scenarios to where they do not have that going on, and they're handling carbon black, they're sanding fiberglass, and it gets interesting out there. I don't like that. So wear a mask, use gloves, under a vent hood for R&D type stuff. Whenever it gets to production, we have ways to integrate into the manufacturing method to where people are not handling powder at, 250, 1,000 kilos at a time. So you're able to actually integrate this into your method and not have to do that.
Okay. Can it increase the O2 CO2 into barrier in polyethylene or polypropylene so that it can replace ML packaging?
Yeah, actually, I have a couple of things off the shelf for that. Yeah, it can do that. Again, it goes all the way back to morphologies, defects, kind of what barrier system you want to do. Molecular sieves, are you looking to, I know specifically you were talking about O2, but when it comes to defects, you can select some, tailor that to where it can start acting as like molecular sieve to everything but hydrogen, or O2, CO2, massive particles, water even, to where it can actually offboard a lot of that stuff. So yeah, it's possible.
What type of graphene can be used to improve friction and wear properties in elastomeric materials?
Ooh. There's a lot of different factors that go into that as well. Reach out to me. I'd love to talk to you about that, because I know elastomeric materials, there's a lot of other chemistries and a lot of other additives that, depending on what elastomer you're using, definitely dictates what graphene and what functionalization you're going to put into that system.
Can you talk about the use of graphene in production with carbon prepreg?
Yeah, successful. Nobody has had any problems prepregging any of our formulations, other formulations on the market. It's really easy. You still mix into this the resin system, prepreg it like normal. We actually have some overseas manufacturers making prepregs with our material right now.
There's a few more here. I'm just going to read them. I think maybe a retread in a couple of spots, but what kind of epoxy system can I use functional graphene for?
Yeah, great question. BPA, BPF, any amine hardener system. It's not tailored to a specific epoxy, a specific hardener. It can work with, it's worked in any of the epoxy combos that we've plugged it into, but depending on what hardener you use, it kind of dictates how much you need to load it in at because of the reactivity.
Have you done studies with epoxies? Can you share some data or tell us about your findings?
Yeah, epoxy wise, let me. Okay, so epoxy wise, this was an epoxy prepreg system that considering they're using a Korean prepreg, we didn't want to have to go through prepregging in their facility, going through the logistics of that. We wanted to test and integrate using a spray system we developed. So we put a functionalized graphene oxide into isopropyl alcohol, put it into a spray gun, and in their paint booth, they sprayed it on there, and we already had it all calibrated and calculated out how many passes meant how much concentration was going on there. So when we went in onto this carbon fiber epoxy prepreg, we got these results. We got increase in strength and sensitivity. Other prepreg systems are experiencing strength increases of anywhere between 35 and 70% increase in flex strength. G1C increases anywhere between, I've seen it as high as 150% increase at a 0.1% concentration. The lowest I've seen on that is 25%, still at that 0.1% concentration. So yes, we have plenty of data within epoxy systems. Reach out to me and we can talk through that.
What type of graphene could be used as an additive to concrete to reduce weight and carbon dioxide, carbon monoxide emissions?
Okay, so let me put the caveat on that one. I'm one of those weirdos that think people trying to get graphene into concrete, it's going to be an uphill battle, because there have been studies done that depending on what the pH of not only your solution, but of the graphene that you put into there, it could totally dictate how it behaves. Not to mention the morphology, the structure, all of that. So as far as I'm aware, the best graphene for concrete applications, it's more of a really bulk graphene. So look up the University of Manchester concrete living lab. I'm pretty sure that's what they called it. They poured a slab outside of University of Manchester just to test how this slab was going to weather. They didn't use rebar. They poured 30% less because in the lab, it showed that the strength properties were much better, the degradation was much better, and so they poured it. And I was there, I don't know, probably a month after they poured it. It set a lot quicker. I'll give them that. 6 months later, I was back, and it looked like it had been there 5 years. It was pitted. It was kind of sunken a little bit, mossy and moldy when I looked at the other concrete around it, and it was nowhere near as that. So it's still a field that everybody's trying to understand and really deploy. Couldn't really tell you much else than that.
Okay. I think that's pretty much all we have time for. I want to assure all of the attendees that if your question wasn't fielded, they will be provided to Kevin, and he can get in touch with you, as well as the ones that there were the follow-up discussions on. So we'll make sure he has your contact info. With that, thanks so much, Kevin. This has been a great presentation, and really appreciate you taking the time to talk about this with us today.
Yeah, thank you guys.
And I'd also like to take time to thank all of our attendees for taking the time to join us. We really appreciate you being here, and hope you'll join us again for the next Composites World webinar. For more information, please visit compositesworld.com/webinars. And thanks. Have a great day, everybody.